Now let's look at few induced norms, examples of few induced norms. First one is maximum column sum. It is normally defined as like this. So note that we've already seen this norm for matrix, which was sigma ij equal to 1 to n modulus of aij. So we're just taking the modulus of all the elements of a matrix and adding it together. This was actually a vector norm, but a matrix norm, but it's a matrix norm derived from a vector norm. This is different from this norm. So take care of the notation. And how we're defining maximum row sum. This is equal to max of. So we are looking at different columns, right? So the columns are actually indexed by j. J is the argument j is actually varied from 1 to n, and we look at every ij. Sorry, we take the column sum of each jth column. The maximum of all such columns will give you the. So what does this mean? We have A1, A2, etc., AN. These many columns. For each column, we find the L1 norm. Each column is actually a vector. We find the L1 norm of A1, 2, etc., AN. Then what we do is we find the max on all these L1 norms. That is the value of the maximum column sum. Okay, now we have to prove that this is induced from. We have to show this is induced from L1 norm. To show that what we should prove, we should prove that maximum column sum of A, so column sum norm of A is equal to max of norm x is equal to 1 norm of Ax, L1 norm of Ax. So we have to prove this. Okay, let's see how we can prove this. True if includes few tricks. So there are two aspects of the proof to prove that this is equal to max of this. First, okay, let's look at it. There are two parts we have to prove this. Okay, let's look at the first part. So for that, we assume we put let A is equal to A1, A2, etc., AN. This is like what we have seen here, like n column vectors stacked together, right? Then by definition, this is max of 1 less than I less than n norm of L1 norm of A1. This is clear. This is by definition of we define here or what we've seen here. Okay. Now let x is equal to x1 etc. xn, x2, etc. xn, which belongs to Rn, then what is norm of Ax by this definition? Okay, this is norm of, and let's look at this definition. You know, A is our vector stacked together. So this is x1 times linear combination of these vectors, right? This is basic matrix multiplication, right hand multiplication of a vector for a matrix. This is x1 a1, x2 a2, etc. plus xn an, right? So if you take can actually this is actually L1 norm, and we can actually apply triangle inequality. Because a sum of norm of a sum is less than or equal to sum of the norms. That's what triangle inequality says, which is less than or equal to x1 a1 plus x2 a2 plus etc. plus this is true, right? Let's write this more compactly and write this as I equal to 1 to n norm of xi ai. This is true. This is just triangle inequality. Since it's a valid norm, vector norm, we can use this triangle inequality. Yes. Now, what we can do, we have a norm and xi. Oh, fine. Okay. So x2 is some scalar, right? So by homogeneity, you can take out xi. This is equal to sigma I is equal to 1 to n norm of xi. This is by homogeneity. So I think till this step, it's clear. Now, this is L1 norm is actually here we are actually what do you call it? Taking taking L1 norm, but instead we can take suppose we take max of it, y equal to 1 of xi. So this was just we replace ai. Instead of that, we replace it with ak, which where k being the maximum. This will be a less than equal to inequality, right? Now, this is a constant. You can take it outside, right? This is equal to max of 1 less than equal to k less than equal to n norm of ak sigma I is equal to 1 to n of xi. This is actually the definition of a1 and this is the definition of x1. So what do we get here? We get norm of a matrix norm of what do you call it? Maximum column sum norm of ax1 is less than or equal to norm of a1 norm of x1, right? But by definition, we have to put x is equal to norm of x is equal to 1, right? So if you put max of norm x1 is equal to 1, oh, I think I missed on the left side. The left side is not, this is not matrix. This is vector norm. Here it is not. This is vector norm. This is less than or equal to, this is equal to 1, right? Norm of a1. This is the first part of our proof. And now we've proved that. What is this? This is less than or equal to the right on the right hand side we have a column sum of a maximum column sum of a norm of a. Prove that this is equal to an induced norm of x1 less than or equal to the induced norm. So if we can prove, now we have to prove is less than or equal to max norm x is only equal to 1. X. We can prove this. Then if this is sandwiched between two inequalities, then both sides being equal, this has to be equal. To prove the second part, to prove this part, let x is equal to ek, where this is canonical vector. Like k is equal to 1, 2, etc. n. So we're taking the canonical vectors. So we have max of, not that this is ek is 0, 0. This is the kth entry, 0, 0. Okay, this is also a valid, it's a feasible vector. It is one of the candidates which can actually optimize this problem. Okay, norm x1 is equal to 1, x1. So what does it do? Sorry. So if we find this, ax1 in this case will be some value ak, sum of ak. Why? Okay, we'll discuss this part.